Good morning. Welcome to Calculus Chemistry 30 in the AM. We're coming to you live and recorded, whatever that may mean. I want you to take a moment right now to jot down this diagram as is. We'll explain it afterwards, okay? You can pause the video because I won't record empty time. So video will be paused. Jot this down. So at this point, I'm recording. I'm assuming you've got this jotted down on a poster. Explain this. Electrochemical cells. Another word for this is batteries. But there's some types of electrochemical cells that don't quite work like batteries. They require energy. Now to explain what we have, let's take a look at these. Actually, I should have dug them up. This is a metal strip here. This is a metal strip here. Right? That's what these are. Okay? This is a wire. Next strip to the other strip. And in the middle, I put this like a meter, you know, like a voltmeter in grade 9. Maybe you guys were sent home, but like really you were with me in my grade 9. Who was it? No, you were. Okay. Anyways, you know what I'm talking about because I know you used it. We had voltmeters and stuff like this. So that's just something, you can put a light bulb in, something that uses electricity. That's what this is supposed to be. Okay? So it's, I don't care where the arrow is. It's just showing that electricity is flowing. And the direction. The electrons, E negatives, flow from left to right in this stuff. Okay? Now, if you weren't sent home in grade 9 in the COVID, you would have learned possibly that electrical circuits must be a complete circle, a loop, circuit. So the electrons come from the strip area, travel through here, but they have to somehow return. That's what this salt bridge is to complete the loop. So that's why we have that salt bridge. Now, if it was just watery, it would run out. So typically you have sort of a gel. And the reason why I use KNO3 as my default salt, because potassium and nitrate, neither one of them makes solids in solution. So you're not going to have unintended solids form, unintended reactions. I give a copper zinc example. It's quite common. What do they call the Duracell battery? Old enough. They used to call it the copper zinc. Then you probably have you ever heard of that? Copper zinc combinations are quite common. There are two reasons. They're quite effective, and the cost. There's other ones that are more effective combinations, but they cost too much. You don't want to make a battery out of gold. Okay. The copper and zinc is a good combo. This is a simplified battery. It doesn't look like a Duracell battery or anything. Those ones are a little more complicated, but the same principles. Okay. Now, what's going to happen is the zinc is eaten away and the copper is formed. So what happens is that after a day or so, you'll notice that this is starting to corrode out. You know, it'll look like it's being rusted away or something. And then the copper will have lumps of copper forming on it in the solution. Okay? Now, a few other things, the vocabulary. Anode and cathode. These are the same as anion and cation as far as charge. So an anion and an anode have the same charge. So what would we put down for anode? I'll give her a name. Anode, anion, or anion. I'll give her a name. Negative. So the anode side is negative. I didn't have you write that down blindly before because I wanted you to read. So that's the negative side of the battery. So by default, the other is positive. And you think cathode? Absolutely, that's the positive side of that. Now, once we have negative and positive, something else makes more sense. Electrons are negatives. Doesn't it make sense that they'd be attracted to the positive side of the battery? So that's why the direction is the way it is. Now, if you put zinc and copper in, though, why is one positive and one? Why couldn't the copper side be the negative? Well, there's a reason. We'll get to that in a little bit, but peel down a bit. We're not ready. So then the next thing, the zinc is eaten away. As the zinc strip is eaten away, the zinc has to go somewhere. So what happens is, as the zinc is eaten away, we get zinc ions in the solution. Okay? And the other solution, more copper is formed. By the way, is that red, guys? More copper is formed? Okay, somehow I can't tell the color. Oh, good. Purple is what I was hoping. This is in a copper solution. This is the way the battery would have to work. So it's the copper from the solution that's deposited on that strip. And we would choose a solution, say, zinc sulfate, copper sulfate. I'll just write that down. So maybe this would be a ZnSO4. This would be CuSO4. Copper 2 sulfate. That's a blue stuff. I had to say that. That's where the ions come from. Now, thinking about the salt bridge, I'll do this one in whatever color this is, purple, burgundy, gold, or whatever. KNO3 is the salt bridge. And well, let's just think about this. K's are pluses, NO3s are negatives. Somehow this circuit has to be complete because you said electrons transfer, so charge is being transferred to this one. And then with the copper ions going on to here, you're screwing up the whole level of charge in that beaker. Okay, so what do you think might have to happen? Well, maybe these K pluses will migrate. And then the NO3s, well, NO3 negatives will come in here to neutralize the Z. You don't have to write that in there, but that's the purpose of the sulfate. It carries charge, or it completes the circuit. We're not going to focus on the salt bridge too much, but no one has to be there to drawing the diagram or labeling the diagram. It'll be on. Okay? Now, I said, how do you decide which one's the anode and which one's the cathode, the zinc or the copper? Here's a memory aid that we're going to use. Red caps. You know how the oil rig? Electrons, actually gaining electrons. Well, red cap is our memory aid. Probably reduction, red. Cap would be anode or cathode. So reduction happens at cathode. It's a memory. It's not chemistry, but it helps you remember. They'll be asking you to decide which is which. And for oil rig, I know reduction is gaining electrons. Reduction happens at the cathode. So let's take a look at this cathode. Cathode. And we'll scroll up again. The electrons, reduction is gaining electrons. The electrons are added or gained that way. that all the rig and the red cap are the same. So, yeah. Now, real quickly, outside of the chemistry classroom, have you ever used the term probably anode more than cathode? Have you ever heard it? Yeah, anode rods. What is the purpose? This is what I was going to get at. Anode rod in the water heater. And every 2 years or so, you replace it because it's being eaten away, just like the anode, the zinc is eaten away too. Exactly. So there's an example of an anode. Sometimes though, when you're talking about batteries and stuff, I've heard people, not any regard to whether it's positive or negative, pitch it up to the anode and stuff like this. People will say that sometimes. That's fine. I never have heard a mechanic refer to a cathode or something like this, like a non-chemistry person. Okay? You might sometimes we'll hear of cathode ray tubes and stuff like this. There's something to that too. That's in physics and chemistry. Okay. So just remember anion, anode, negative, because you should know those words. Cathode, cat, ion, positive. Okay. Now we're going to add something underneath here. Because if there's reduction and oxidation going on, this is why this is part of the redox. We can figure out some half reactions. And we're gonna. Now this particular one, red cap, we already know the cathode instead of the reduction. So the reduction half reaction is going to be the one that we call. So write it as a reduction line and scroll up. Color that I use, red, or I use red. The reduction half reaction. If it's adding electrons, it has to be the charged copper ion. Depositing copper. That's reduction. Reduction is meaning electron. Information we've already figured out. Yeah. Then obviously the zinc is the oxidation center. We don't have a memory because no reduction happens at the cathode. Oxidation happens at the anode. So in that one, we have the zinc being eaten away. I think we're using green on those. So we have zinc being eaten away as the ions go solution. Hey, this is a pretty easy reaction to add up, eh? Oh, 2E negatives. Oh, right. Oh, yeah. So, we'll get to how to predict how much voltage you get later on. But right now, I just want you to realize that the electrons are going from one side to the other. And this is a simple wet cell. You ever hear of batteries referred to as dry cells? Okay. That means a Duracell battery, calculator, and stuff like this. I can tip it, it won't spill out. You're familiar with wet cells in one application. Not, maybe you didn't know this though. Car batteries have sulfuric acid and lead plates and stuff in there. So never, first of all, with a car battery, because it's an acid stuff, do not tip them over and stuff. They're not designed to be tipped upside down and stuff. Usually nowadays they're contained quite well. They probably won't spill. I remember one time when I grew up on a farm, we had some old batteries and stuff, and they frozen over the winter, they cracked and stuff, and I carried them out, whatever. And it got on my clothes and stuff. My clothes within a week were like they had big holes in them and stuff like that. Just whatever. My skin wasn't too irritated. Yeah. So there's acid. Those are wet cells. They're not designed quite as simple as this, but it's along these lines. That's some vocabulary stuff that I'm going to pause and let you jot down. Some of this we already have. If you don't feel you need to rewrite cathode, red cat, go ahead. But you guys are young adults, though, so you know how you learn. So I'm going to pause the video. You can summarize this electrochemical cell here. Write down what you think you need to know. So, summary of the electrochemical cell stuff. Anode, site of oxidation. It's the strongest reducing agent. It's oxygen. It gives away electrons. That's why it's negative, giving out negative electrons. There you go, negative charge. Cathode, red cat, site of the reduction half reaction. It's accepting because it's positively charged. It accepts or attracts electrons. If electrons are flowing, you have an electrical current. That's electricity. Chemistry meets physics. The ions in the salt bridge. The anions go to the anode. And I kind of talked about that a little bit. And the cations go to the cathode. Use a salt that doesn't form precipitates. And I told you, my default is KNO3. It could be sodium nitrate. Whatever. I just tend to put down KNO3. Okay? So, the electricity part of this now. Voltage calculations. Jot this down. We'll go over this. This shouldn't take you too long to jot down. Okay. So, what's the charge of that copper zinc battery that we did the diagram? Well, we already know the half. So what we need to do is list them up. And I'm assuming we kind of remember what we did that. So here's the reaction. I'm going to list them. I forget which one. I'll go with zinc. And copper. Okay. This one is an easy half reaction to balance because it just has electrons, no oxygen or hydrogen. I'm going to pause for a second. Okay, zinc. This is easy to balance. We've already seen it. Two electrons, now zero on both sides. High side down on the low side, so two electrons. This is an easy one in the sense that we don't even have to multiply to balance the electrons. But here's the new thing. You've got to figure out what the, and I'm going to squeeze it in over here. Now this is not going to put a comma there. I don't usually do this. You've got to figure out how many volts this contributes. You've got to figure out how many volts this contributes. So I'm putting an E with like a degree sign on there. Okay. We have to have a way of figuring out where that comes from. I'm going to bring it up on my board, so I'm going to pause this. Bring up my sheet and I'll show you where it is on your sheet. We look up the voltage on this handout set that you guys have. Chemistry finals, where I guarantee you'll use it. Otherwise, you may never use this ever again. I use this stuff every day. This chemistry teacher. Yeah. It's about it. No, it is. Yeah. But hey, it's the same with all kinds of things. I have no crystal ball to tell you that you'll do this or that in 10 years. You probably won't. If you go into nursing, you're not going to be balancing equations. Help you. However, I have a job to do, and it's to convey this information. Then you guys have a job to do to somehow communicate to me that you understand something. Okay. Hey, I'm recording. Zinc. The zinc 2 plus. So here's what we do. We go to our sheet. We look up the zinc 2 plus. So you're on the voltage, standard electrode potentials for half reactions. You'll notice something though, that they're all written with the electrons on the left side. Okay. Now I'm looking, and I eventually find the zinc plus 2 electrons gives me zinc. So you see that there? I'm not going to highlight for the video just because it's working. But it's right around, I guess it does. There is the zinc. Now that's zinc 2 plus going to zinc solid, negative 0.76. Now I'm going to flip that. Is that written the same way? No. So when you flip a reaction, you flip the sign. Or no, was it the same way? It wasn't. So we're going to pause the video and come and see, guys. So when we looked that up, it was negative the way it was written, but the reaction flips. We flip the positive 76. That's so I want you to put the positive or negative sign in there. I know it's assumed if you don't have a sign. And B for volts. Notice that. And it says so. Then we look up the copper one. The copper one will be written as is. They're all reductions. So let's take a look at the copper reduction reaction. But keep in mind there's two different coppers, copper 1 and copper 2. So we have to look up the copper 2. I see a third from the top. Right? Positive 34 the way it's written. Okay? I got to put that down. Positive decimal 3 volts. Now the rest is arithmetic. Use a calculator, but the overall voltage of the cell, the net 1.10 volts. Now this is easy here, but I'm still going to get you to do it. Adding up the two half reactions, 2 electrons cancel 2 electrons, and it just, we already had this at the start. To show that you've shown this correct. Okay. Right? Arithmetic is a ton. So this people find it easier than balancing the redox equations that we've done last week. That's probably the toughest part of it. This part isn't too bad. So voltage calculation. Oh, I want to point out something on the sheet. This is under certain conditions, certain temperatures and solutions. At the top of your voltage sheet, that E0 means these conditions are met. Standard electric. The ion concentrations in solutions are 1 mole per liter. That's what it says at the top. In water, and it's 25 degrees Celsius. And you've probably known this too. When batteries are cold, they don't work as well, right? So it's not 25 degrees Celsius. So this is a very alter these voltages by having different concentrations of solution and different temperatures conditions. Okay? All ions are aqueous, it's assumed. So that's that. So I want you guys to jot these down. You can reference them. It's from a different book though. Page 642, 3ABC. Calculate the voltage of these 3 overall. So write down the questions and then we'll get to doing them after. Okay? I am anymore. Aren't I? I'm going to look up one of these. I forget which one is on that handout set. But it's not cool. Okay, I'm going to pause this. You write down the. Yeah, I just looked it up. This particular item, or the voltage sheet that I gave you didn't have this, so I'm going to just jot this down here. You'll need it for A. So the half reaction, double checking here. No, the cobalt is. So to do that one, I'll give you the voltage for the cobalt. I'll start it up. I'll put it in 3A. Start it. 1.5 reactions. And this, you normally look up on the chart, but this one isn't on it, 0.2 amp. Okay, there we go. That gets you started. You can do all of the others are on the sheet. Last bit of the recording. You guys got some homework. Do these. We'll take them up. Start the next class.